So now you can all see the screen shared by Chengchun. Without further ado, let's welcome Chengchun to give us the very interesting talk about statistical inference in reinforcement learning.
Thanks, Dr. Song, for the very nice introduction, and thanks, Dr. Zhu, for the invitation. And thanks everyone for coming to this seminar. And it is an honor for me to give a talk here to present some of my recent research on reinforcement learning. So just to warm up, in terms of reinforcement learning, I guess one of the most successful application that reinforcement learning algorithms have been made in the recent years will be the development of AlphaGo, which is invented by the Google DeepMind team. And 4 to 5 years ago, it successfully defeated Ke Jie, who was the final boss of the game of Go at that time. And in addition, in the recent years, all those reinforcement learning algorithms, they have been widely applied in a wide variety of applications. So including games, mobile health, ride sharing, robotics, finance, automated driving, etc. And I just want to briefly highlight that in the current computer science literature, in the machine learning literature, most of the papers, most of the works focus in online video games. But in today's talk, our focus will be on mobile health and the ride-sharing applications. So firstly, let's talk about the applications in mobile health. So in recent years, due to the use of cell phones, computer tablets, and some wearable devices in healthcare applications, so those mobile health applications recently emerged. And an example is given by the management of patients with type 1 diabetes, so which is a disease that will prevent patients from producing enough insulins in their body. And because of that, patients will need to constantly inject insulin doses to keep their glucose levels within a certain range. So the subject in the study will be the patients with type 1 diabetes. And usually when those patients, when they have meals, when their blood glucose levels increases, so that's the usual signal to indicate that they should receive insulin doses. And the idea here is to apply reinforcement learning algorithms to capture those signals to help improve the patient's health status. And there are also publicly available data set that allows us to do this kind of research. So for instance, we have data from the Ohio T1DM data set that contains measurements from 6 patients over the 8 weeks period. And the plot here shows the data from one of the patients. And next, I want to talk about the applications in ride sharing. So in terms of ride sharing, you can think about large ride sharing companies such as Uber, Didi Xuxing, or Lyft, and where they have like a group of drivers that operate in a taxi-like fashion. And for this particular ride sharing company, you can see that it has like over 5 million users. And the vehicle trajectory data that they collected per day, they collected each day is over 100 terabytes. So those companies, they do have a huge database. So the richness of the data in those companies provides us with statisticians and as well as computer scientists with very unique opportunities to conduct data-driven statistical analysis. And here are just some of the questions that of the company's interest. So firstly, we have supply-demand forecasting. In particular, at a certain time in the future, in a particular area, so what is the predicted number of call orders, and what is the number of available drivers at that time? So that corresponds to the problem of supply-demand forecasting. And also policy evaluation. After we propose a new policy, how can we evaluate its performance? And policy optimization. So how can we optimize, how can we estimate an optimal policy based on the observed data? And solving these questions require knowledges from experimental design, spatial temporal modeling, deep reinforcement learning, and graphical modeling. And these questions are at the intersections of statistics, computer science, operational research, and machine learning. So the projects that I'm going to talk about in this talk are motivated by these applications. And as the title of the talk suggests, today we will mainly focus on statistical inference in reinforcement learning. So as a statistician, there's a question that always jumps into my mind. So that is statistical inference useful for reinforcement learning or not? And the answer is, of course, yes. And in today's talk, in particular, in the first project, I will convince you that how classical statistical inferential procedures, such as hypothesis testing, can help improve the performance of state-of-the-art reinforcement learning algorithms. So I will first talk about the first project that I'm going to talk about is based on one of our paper published in ICML 2 years ago, where we propose a test for the Markov property in sequential decision making to investigate the goodness of fit of a Markov decision process model. So in case some of you are not familiar with reinforcement learning, so just to give you some background. Reinforcement learning is concerned with solving sequential decision-making problems. And it is typically assumed that there's an agent that tries to learn and interact with a given environment. And at each time point, the agent will observe some features from the environment summarized into a state vector ST. And then the agent will choose some actions among the class of available options. And then the environment will respond by providing the agent with an immediate reward RT. And in addition, the environment will move into a next state. So such a procedure applies sequentially. So at the end, the agent will receive a sequence of the rewards. And the objective of reinforcement learning is try to find an optimal policy to maximize the cumulative reward that the agent receives. So at each time point, the agent will implement a mapping from the pi t from the observed data to a probability distribution over the actions. So to indicate which action that the agent will select at that time. And the collection of those mappings, pi t is referred to as the agent policy, and we use pi to denote the collection of these mappings. So at each time point t, so basically pi t maps the observed data history S bar into a probability function over the action space. So here, the notation ST bar is to denote the set of the observed state action pairs up to time point t. And such a definition of the policy is very general, and we refer it to as a history-dependent policy. So this is because pi t generally depends on the entire data history. Now, suppose at each time point, pi t depends on ST bar only through the current state vector ST. So in that case, the resulting policy is reduced to a Markov policy. Now, suppose pi is Markov, and additionally, all those mappings pi t, they are homogeneous over time. Then the resulting policy is reduced to a stationary policy. So just to recap, so most generally, we have the class of history-dependent policies. Now, if those policies, they are no longer history-dependent, then we get a much smaller class of policies, so which corresponds to the class of Markov policies. Now, on the top of that, suppose all those time-dependent mappings, they are stationary in time, so they are time homogeneous. Then we get an even smaller class of policies, which corresponds to the class of stationary policies. And the reinforcement learning is basically concerned with solving sequential decision-making problems. And here, this is the some of the state-of-the-art reinforcement learning algorithms. But what I do want to highlight here is that the foundations of all those reinforcement learning algorithms rely on modeling the observed data process by a Markov decision process model. So under such a model assumption, it ensures that the optimal policy is a stationary policy. It is not a history-dependent policy. And this greatly simplifies the calculation because there's no need to focus on the class of history-dependent policies, so which is a huge policy class. We only need to restrict our attentions to the class of stationary policies, so which is a much smaller class of policies. And what underlies the Markov decision process model assumption is Markov assumption, so which intuitively means that conditional on the present, the future, and the past, they are independent. And suppose if we assume the reward is a deterministic function of the current state action pair as well as the future state, then it suffices to test whether the future state is conditionally independent of the past state action pair given the current state action pair. And additionally, it is also assumed that the Markov transition kernel shall be homogeneous in time. So here's a graphical illustration of the Markov property. So conditional on the current state action pair, the reward and the future state, they are independent of the past data observations. So they are independent of the past data sets. Now, given the observed data, of course, there are data generating process that satisfies this model assumption, but there are also data generating process that does not meet this requirement. And here I list some of the ARL models that we can potentially consider to model a given offline data set. Now, in the first model here, the MDP assumption is directly satisfied. So if we know that the data satisfies this assumption, then we can directly apply existing reinforcement learning algorithms to this observed data set to derive an optimal policy. And in the second model here, the Markov assumption is not directly satisfied. So in this case, although the model is not directly an MDP, it is a high order MDP in the sense that suppose we concatenate st at-1 and st-1. So suppose we concatenate those three variables together to construct a new state vector. Then the resulting MDP assumption will be satisfied on the transformed data process. So given an offline data, if we know that it follows a high order MDP, and if we know the order of the MDP model, then we can first do the corresponding data transformation and apply existing reinforcement learning algorithms to the transformed data set. So this ensures the estimated policy will be optimal. And finally, in the third model here, it corresponds to a POM-DP. So in this case, there were some state variables that are hidden and cannot be directly observed. And no matter how many past observations we concatenate together, the Markov assumption will always be rejected. And in the literature, in this case, there are algorithms specifically designed for POM-DPs. And if we know data follows a POM-DP assumption, then we should use those algorithms for policy optimization. So I just want to first briefly summarize the contributions of our paper. So methodologically, we propose a forward-backward learning procedure to test the Markov assumption. And later I will discuss in detail what this forward-backward learning procedure means. And to our knowledge, this is the first work on developing consistent test for the Markov assumption in reinforcement learning. Now, based on the proposed test, very importantly, we can sequentially apply our test for ARL model selection. So particularly for a given data set, what we will do is that we will first apply our test to see whether the data satisfies the MDP model assumption. And if the hypothesis is satisfied, then we can directly apply reinforcement learning algorithms to this data set to estimate an optimal policy. Now, otherwise, we will sequentially apply our test to see whether if it is a second order MDP, a third order MDP, etc. And suppose we found out that a high order MDP assumption is satisfied, then we will do the corresponding data transformation and then apply existing reinforcement learning algorithms. And finally, suppose we apply our test multiple times and it always rejects the null hypothesis, then we can conclude that the model will be a POM DP, and we should apply algorithms from the POM DPs for policy optimization. And such a procedure will be critical in offline domains. So this is because for a given offline data set, without any prior knowledge, we really do not know which model will describe this data set best. So suppose we work with an underfitting model, then any stationary policy is not optimal. And if we work on overfitting model, then the estimated policy will be very noisy due to the inclusion of the many irrelevant lagged variables in the data set. And empirically, as I will show you in the next slide, we will show our test. We will show how our test can help identify the optimal policy in high order MDPs, and it can also help detect POM DPs. And finally, theoretically, we show that our test can control the type 1 error under a bidirectional asymptotic framework. And later, I will discuss what this bidirectional asymptotic framework means, but it is a very natural framework for reinforcement learning. And I just saw a question in the chat from Peng. Is it a fixed length vector when we concatenate the previous S prime and A prime? Say if the fixed length is 3, we call it a third order MDP. Yeah, so very similarly. So for instance, if it is a third order MDP, then we should concatenate the previous 3 states and the 2 actions to construct the new state vector. Does that answer your question? Okay, so let's first revisit our mobile health applications to illustrate the usefulness of our proposed test. So we consider the data from the Ohio T1GM dataset, which contains measurements for 6 patients with type 1 diabetes over 8 weeks. And we divide each follow-up day into 1 hour time interval. So at each time, during each time interval, we will need to decide whether to inject insulin for a given patient or not. And the state variable corresponds to the patient's time varying variables, including their blood glucose levels, their food intake, their exercise intensity. And the action is to determine whether to inject insulin or not. And the reward corresponds to the index of glycemic control, which measures the patient's health status. Now we did 2 analyses based on this data set. So in the first analysis, we sequentially apply our test to determine the order of the MDP model. And we conclude that it is a 4th order MDP. So what it means is that, roughly speaking, the observations collected 4 hours ago, they are independent of the observations collected 4 hours later, given those observations collected within this 4-hour time interval. So that's an interpretation of this result. And in the second analysis, we further split the data into training testing samples. And then based on the training data set, we apply existing policy optimization procedures using FIDQ iteration to estimate an optimal policy by assuming that the data actually follows a case order MDP model for K ranges from 1 to 10. And next, on the testing samples, we apply existing policy evaluation method based on FIDQ evaluation to evaluate those estimated optimal policies. Now, both FIDQ iteration and FIDQ evaluation requires to model the Q function and to allow for flexibility with a random forest model to model the Q function. And now, as you can see from this table, it follows that the value of the estimated policy, by assuming it is a 4th order MDP, reaches the largest value. So this suggests that our procedure can be naturally coupled with the existing state-of-the-art reinforcement learning algorithms to improve their performance. And we also apply our test in POM-DP applications. So this is a very simple toy example, the tiger problem. And basically, there are two doors here, and there's one tiger that lies behind one of the door. And at each time point, we can choose like which door to open. So if we open a door and there's a tiger that lies behind it, then we will receive a huge penalty. Now, suppose we open a door and there's nothing behind that, then we will receive some reward. And in addition to these two actions, we can also choose to listen to infer the location of the tiger. But listening is not always 100% correct. So there are some noises during the listening process. And it is due to those noise that make the data generating process as a POM-DP instead of a MDP. So we first apply our test to test whether it follows a case order MDP model. So since it corresponds to a POM-DP, then we expect the null hypothesis should be rejected. And it can be seen from the first plot that our test has good power properties. And we also did a second analysis based on this data set by including the true location of the tiger in the data. So if the location of the tiger are known to us, then the data basically becomes an MDP. And it can be seen from the second figure that most of the empirical rejection rates, they are within the Monte Carlo error bound, so suggesting the validity of our test procedure. So finally, I just want to briefly talk about the methodology of our work. So as I have mentioned earlier, this is the first work to test the Markov assumption in sequential decision-making. So although there were no prior work in reinforcement learning, but there are some existing approaches for testing the Markov assumption in time series. And in particular, this work by Chen and Hong, they proposed to characterize the Markov assumption based on the notion of conditional characteristic function. And then they proposed to use the local polynomial regression to estimate those CCF functions. Now, although those local polynomial regression, they work well in fixed dimensions, but they will perform poorly in high dimensions. So the major challenge here lies in developing a valid test for the Markov assumption in moderate or high dimensional settings. And this is typically the case because the dimension of the state will increase as we concatenate measurements over multiple time points in order to test a high order MDP. And this motivates our forward-backward learning procedure. And here's a summary of some of the key components of our algorithm. So firstly, to deal with high-dimensional state space, we employ modern machine learning algorithms to estimate those CCF functions. And the key idea here is to learn two CCF functions. So we first learn a CCF function of the future state given the current state action pair. So this corresponds to a forward prediction task, and we refer to the resulting estimator as a forward learner. And additionally, we also propose to learn a CCF function of the current state action pair given the future state action pair. So this corresponds to a backward prediction task, and we refer to the resulting estimator as a backward learner. And we further develop a random forest Bayesian algorithm to estimate those CCF functions and borrow ideas from the quantile random forest algorithm in order to facilitate the computation. Now, those machine learning algorithms, although they work desirably for the purpose of prediction, but they might not be desirable for the purpose of conducting statistical inference. So due to the large bias of those algorithms. So to alleviate the bias of those machine learning algorithms, we propose to construct a double robust estimating equations by integrating both the forward and backward learner. And to improve power, we propose to construct a maximum type test statistic and use multiplier bootstrap to control the type 1 error. And this is a summary of the algorithm. And due to the time limit, I will just skip this slide. And finally, let me briefly talk about our theoretical results. So we established a bidirectional theory for our proposed test. Now, if we let capital N to denote the number of trajectories in our observed data set, and capital T to denote the number of decision points each trajectory. Then the bidirectional asymptotic framework is basically a theoretical framework that either allows capital N or capital T to grow to infinity. Now, if we restrict it to our real data set in the Ohio T1DM data set, we only have 6 patients. But for each of the patients, we have a relatively long trajectory. So this corresponds to the setting of large T and a small n. But there are also some other mobile health applications, such as this intern health study, which I also currently work on. It has a large number of patients, but for each patient, the time points is not that many. And of course, in applications in games, both capital N and capital T will diverge to infinity. So if we propose a method and if we want our method to be generally applicable, then it should be applicable to all those 3 scenarios. So under certain conditions, we show that our test can control the type 1 error under such a bidirectional asymptotic framework. So as either capital N or capital T diverges to infinity, our test is valid. So this concludes the first project. And in the second project the second project that I want to talk about here is based on one of our recent paper accepted in JASA, where we propose a reinforcement learning framework to evaluate dynamic causal effects in A/B testing. So in terms of A/B testing, it now has become like a golden standard for industrial, for technological companies to compare 2 versions of the policies. So what those high-tech companies will usually do is that they will randomly allocate visitors to 2 different treatments. And then based on the results, usually they will just conduct a very simple 2-sample t-test to see whether the new policy is better than the old policy or not. And in this project, we mainly focus on the order dispatching problem in ride-sharing companies. So order dispatch is like one of the most fundamental problems in a ride-sharing company. So basically, the problem can be formulated as follows. So at each time point, the company will receive some call orders, so a list of orders. And at the same time, we will have a list of available drivers. The problem is that for each potential order, which driver shall we send to pick up that particular order? So that corresponds to the problem of order dispatching. And this project is basically motivated by the need for comparing the long-term rewards among different order dispatching policies in ride-sharing companies. And there are basically 3 key challenges here. So the first challenge is due to the existence of the carryover effects. So I will show you in the next slide that the carryover effects naturally exist in our applications. And most of the existing A/B testing procedures cannot be used to detect such carryover effects. And typically, the company would like to use an alternating time interval design to conduct the online experiment. So typically, what they will do is that at a certain time point, they will first use the old policy, and then switch to the new policy, and then switch back to the old policy, so on and so forth. So under such an alternating time interval design, past actions will affect the future outcomes. So when developing an A/B testing algorithm, it is very important to capture such carryover effects in order to compare the long-term rewards. And the second challenge corresponds to the need for early termination. And this is because each experiment will take a considerable time. And the early termination is very important in order to save time and budget. so this is because in the company, they have like a lot of experiments in order to be conducted. And the third challenge comes from the need for adaptive randomization. So it would also be beneficial if we can maximize the total reward or detect the alternative hypothesis faster during the online experiment. And to our knowledge, no existing test can address these three challenges simultaneously. And here's a simple illustration of the carryover effects. So how past actions can affect the future outcomes. Now, suppose we have at a certain time point, we have a core order appearing in zone number 1. And at this time point, we have two actions that can be used. So we can either ask the driver in zone number 3 to pick up that particular order. Or alternatively, we can ask one of the driver in zone number 4 to pick up that order. Now, suppose we ask one of the driver in zone number 4 to pick up this order, to pick up that passenger. So this will leaves two available drivers in zone number 4. Now, in the near future, so we receive a lot of orders in zone number 8. So at that time point, we can of course ask two drivers in zone number 4 to pick up two orders here. And we can also ask the driver in zone number 3 to pick up one of the order. But due to that, zone number 3 is very far away from zone number 8. So the passenger might just refuse to wait. And because of that, we will lose a potential order in the future. Now in contrast, suppose we ask the passenger in zone number 3 to pick up the passenger in zone number 1. So this will save all the 3 drivers in zone number 4. So later in the future, if there's a lot of orders arriving in zone number 4 or in zone number 8, then we can ask all those 3 drivers in zone number 4 to pick up 3 of the orders here. So this will give us a better, larger future reward. And this is just a very simple illustration to show the existence of the carryover effects. So why an action at the past can affect the outcomes in the future in our applications. On the contrary, many of the existing A/B testing procedures, they cannot detect carryover effects. So to illustrate, we designed some very simple toy examples. So in the first example here, so all those observed data, they are independently generated. So we expect most A/B testing procedures would work under this example. And in the second example here, the immediate reward is equal to the current state variable. So in this case, there are no short-term treatment effects under this example. But the reward, the current reward will be affected by the past action. So in this case, the carryover effects exists. Okay? And the data generating process, they are no longer independent over time. So we apply a two-sample t-test and a double machine learning-based test, as well as our proposed test to test the difference between the long-term effects under these two examples. And in the first example, where the data are independently generated, so all those 3 tests, they have good power properties. But in the second example, when the carryover effects exist, so we can see that both the t-test and the double machine learning-based test, they do not have any power at all. On the contrary, the proposed test is still able to detect the alternative hypothesis. Now, next, I just want to give you a summary of the contributions as well as the advances of our proposal. So firstly, we introduce a reinforcement learning framework for A/B testing. So this is in order to address the challenge of the carryover of the existence of the carryover effects. So basically, what we will do is that instead of modeling the data generating process as an independent process, so we model it using the Markov decision process model. So under such a model assumption, as you can see here, the past actions will not directly affect the future outcome. However, it has an indirect effect on the future outcome through its effect on the current state vector. So what it implies that in practice, if we use such a reinforcement learning framework, we should carefully choose the state variable in order to include all those important mediators between the past actions and the future outcomes. And secondly, we also propose a value testing procedure for detecting the value difference between two policies. And the proposed test has three novelties, including sequential monitoring on updating, and it is also applicable to a wide range of designs, so including the Markov design, the alternating time interval design, as well as the adaptive design. And here's a summary of the method and the series of our projects. So the first step of our proposal is to apply the temporal difference learning procedure to evaluate the difference between the value difference between two policies. And we also provide valid uncertainty quantification based on one of my recently accepted JRSB paper. So since we need to conduct, since we need to do hypothesis testing, so we need to compute the p-value. And the second key component of our proposal is to adopt the alpha spanning approach. So in order for for the purpose of sequential monitoring. So the alpha spanning approach is originally proposed in the classical random clinical trials for sequential testing. And the third key component of our proposal is to develop a bootstrap-assisted procedure for determining the stopping boundary. So this is because the alpha spanning approach uses the numerical integration method, but the numerical integration method is no longer work here in our application in the adaptive design due to the existence of the carryover effects. So informally speaking, we can show that our proposed test can control the type 1 error and is able to detect the alternative hypothesis that converges to the null at a parametric rate under the Markov design, the alternating time interval design, as well as the adaptive design. And here are some simulation results where we applied the proposed test with a very simple two-sample t-test. And as you can see from the result here, that the two-sample t-test does not have any power at all. So as we have mentioned, this is because it fails to detect the carryover effects. So it requires the data generating process to be independent over time. And to the contrary, the power of our proposed test remains very powerful. So finally, we apply our proposal to a data set from the ride-sharing company. So basically, the data is collected from a given city in a given time period. And the experiment lasts for 2 weeks. And we choose to select 30 minutes as one time interval. So this gives us a total of like over 600 number of observations. And the state vector includes 3 variables, so including the number of drivers and the number of requests. So those 2 variables serves as the supply and the demand, and they are well known to have huge impact on on the immediate reward. And additionally, we also include a supply-demand equilibrium matrix, so which serves as a mediator that mediates the treatment effect of the past actions on the future outcomes. And we compare the performance of a new policy versus the old policy and choose the driver's income as a reward. And the new policy is expected to have better performance in practice. So we first apply our test to a data set from an AA experiment, so which basically compares a baseline strategy against itself. So this is just used as a sanity check in order to check the validity, whether a test can control the type 1 error or not. And it can be seen from this figure that the rejection boundary, so the blue line here corresponds to the stopping boundary, it is always above the test statistic. So we fail to reject the null hypothesis on the in this AA experiment as expected. So this suggests that our test can control the type 1 error in practice. And in the second experiment here, we apply our test to data from the AB experiment. And it can be seen that our test is able to conclude that the new policy is better than the old one before the experiment ends. So this demonstrates the usefulness of our test in real-world applications. And we also apply the very simple two-sample t-test to the AB experiment, and it fails to reject the null hypothesis with a p-value 0.18. And as I have mentioned, this because the two-sample t-test, they fail to capture the carryover effects. So this concludes the second project. And due to the time limit, I guess I will just very quickly to go through the third project. The third project is based on one of our recently accepted paper in ICML last year, where we propose a deeply biased off-policy interval estimation procedure. So in this project, we consider the problem of off-policy interval estimation. So the objective is to evaluate the impact of a target policy offline using historical data set generated from a different behavioral policy, as well as to provide rigorous uncertainty quantifications. And here I just want to highlight that most of the existing methods focus on providing point estimators only. But our focus is not only to provide a point value estimator, but as well as to construct the confidence intervals to quantify the uncertainty of this value estimator. And the main idea here lies in developing a deeply debiasing process. So this is an illustration of our proposal. So basically, for any estimator, we know that any estimator, they suffer from a bias variance trade-off. So suppose our focus is to, suppose our focus lies on prediction. So in order to minimize the mean square error of a given estimator, then we require the bias and the variance to reach a balance in order to minimize the mean square error. But here, since our focus is to provide a rigorous statistical inference, so we will need to ensure that the variance of the value estimator should dominate the bias of the value estimator. So that's why we propose such a deeply debias the procedure to iteratively debias the bias of the initial Q estimator. So after applying our deeply debiasing process, it guarantees that at the end, the bias of the resulting value estimator will be smaller, will be dominated by its variance, so that it is possible to construct confidence intervals to quantify its uncertainty. And also the proposed confidence interval is valid under minimal requirement of the initial Q function estimator. So that's all for my talk today. Thank you very much for listening. And the papers and the softwares of my talk can be found on my personal website. Again, thank you very much. Happy New Year.
Thank you, Chengchun. Zhenglin, do you want to take over? Hi, Zhenglin.
Hi, I'm here. I cannot share my screen. Can you give me the right to share the screen?
Jerry, can you please give Zhenglin?
Oh, now it seems that I can share my screen. Can you see my screen now? Thanks. So let me start. So thank you for having me here to discuss Chengchun's nice talk on statistical inference in reinforcement learning. My name is Chengchun Shi, and I'm an assistant professor at George Washington University. So before discussing Chengchun's talk, I want to point out this New York IPS 2021 outstanding paper called Deep Reinforcement Learning at the Edge of the Statistical Precipice. And the goal of this paper is to use empirical study to demonstrate that the point estimates in reinforcement learning numerical studies is not enough. As they say in their abstract, most published results on deep RL benchmarks compare point estimates of aggregate performance, such as mean and median scores across tasks, ignoring the statistical uncertainty implied by the use of a finite number of training runs. And this raises a lot of risks and concerns. They also examine the number of simulation runs over different popular machine learning algorithms in the past 20 to 25 years, and back to 90s when the first TD learning or temporal difference learning method was proposed. The authors conduct about 100 number of simulation runs to demonstrate the effectiveness of their methods. However, as time evolves, the number of simulation runs is surprisingly decreasing. And if you look at the popular methods developed in the past 5 to 7 years, you will find that the number of simulation runs in their papers is about 5. And the main reason why they only conduct very few number of simulation runs is because the simulation environments and the tasks are more and more complicated. And it usually takes days, weeks, or even months for them to run their algorithm for one single simulation study. And this raises concern in reporting only point estimations in their papers. And as stated by the author of this paper, they also conduct a case study on Atari benchmark, and they find that substantial discrepancy between conclusions drawn from point estimates along versus a more thorough statistical analysis, which involve statistical uncertainty quantification. Therefore, they call for a rigorous statistical analysis in RL community. And I think it's a great opportunity for statisticians to contribute their knowledge. And I'm excited and glad to see that Chengchun and his co-author has already made substantial contribution towards this direction. Okay, so next I would like to briefly summarize Chengchun's talk. In the first part of his talk, Chengchun and his co-author developed a forward-backward learning method to rigorously test the Markovian assumption behind the data. And the foundation of many RL reinforcement learning algorithms is the Markov assumption. However, in practice, we don't know whether the data will satisfy this assumption. So it is necessary to develop a statistical test to demonstrate whether the data will satisfy a certain order of Markov property. In the second part of Chengchun's talk, Chengchun and his co-authors proposed a practical reinforcement learning approach for A/B testing to compare a long-term effects between two strategies. One is old, the other is new, to demonstrate whether the new policy will be better than the old one. And they also apply their algorithm in the rideshare company in order to improve the business operations. And in the last part of Chengchun's talk, Chengchun briefly mentioned their recently developed method to for constructing an efficient, robust, and flexible confidence interval for value of a target policy, and shows after looking at their paper, we can find that their method shows a very nice finite sample performance. Okay, and let me also summarize the contribution of Chengchun and his co-authors' works on this paper. And in the first part of in the first paper, basically Chengchun and his co-author developed a doubly robust statistical hypothesis testing to test whether the data will satisfy certain order of Markov property. And because in order to achieve this goal, we have to aggregate states and actions across multiple decision points, then we cannot avoid handling the high-dimensional states and action space. By developing a doubly robust statistical hypothesis testing, and they are allowed to incorporate many different flexible machine learning models in order to handle the high-dimensional states and action space, which are very appealing. And they also develop a bidirectional theoretical guarantee for their hypothesis testing procedure. And this is very important, especially in the offline reinforcement learning. In some scenario, often the number of episodes is quite limited, but the length of horizon could be very large. So in addition to large sample theory, we do need to require theory in terms of the length of horizon. That's the key. So this is why they develop a bidirectional theory to guarantee their methods, the validity of their method. In the second part of Chengchun's talk, they develop a reinforcement learning approach for A/B testing to test whether the long-term effect of one policy is better than the other. And their hypothesis testing procedure allows sequential monitoring and online updating and can be fit into different experimental designs and also allow early stop. They apply their algorithm in ride-sharing company and show its advantage. And in the last part of the Chengchun's talk, Chengchun and his co-author make use of semi-parametric statistics, especially the high-order inference function, to develop a valid statistical inference for the value of target policy, which shows a very superior finite sample performance. So during the reading of Chengchun's paper, I have several general questions. The first question is related to the deep neural network. As we know that in ARL community, implementing deep neural network models is a routine. So how to incorporate deep neural network models in statistical inference and hypothesis testing is an inevitable task in reinforcement learning. And my second question is related to the cross-fitting. And we use many different doubly robust estimator, especially in the offline reinforcement learning. However, if we do the sample splitting in terms of the number of episodes, that's the number of trajectories, it may cause instability. So maybe more efficient cross-fitting over time horizon is needed. And my third question is related to the choice of the discount factor gamma. As we know that gamma can balance between the immediate rewards and the long-term effect. If we want to test whether a new policy has a better long-term effect over the old policy, we are supposed to choose gamma to be very large. However, by using a large gamma, it will create difficulty in estimation of value. If we if we choose gamma to be small, it will make this estimation problem much simpler. However, by using a small number for gamma, it will prevent us to detecting the signal of the long-term effect, as we know that using smaller gamma will weigh more on the immediate rewards rather than the long-term effect. And my fourth question is related to the hyperparameter tuning and model selection in reinforcement learning. I think this is an open problem in this community. And the hyperparameter tuning or more general model selection is much more challenging than the standard supervised learning, because in ARL, there are a lot of quantities which cannot be observed, and therefore we cannot implement the cross-validation procedure because we don't have a target. So it is necessary to develop a new methodology and theoretical guarantee. And my last question is related to the statistical inference for optimal value under UCB or Thompson sampling. And I know Chengchun and his co-authors have already made some contribution along this direction, mainly focused on the epsilon gradient. I want to know whether you have some comments about statistical inference related to the other two popular online algorithms in reinforcement learning. And that's all. Thank you very much.
Thank you very much for Jenny, for a very nice for a very nice summary, as well as those insightful questions. So maybe shall we go by these questions one by one to talk about maybe how to address these questions?
Yeah, feel free.
Yeah, so the first question regarding statistical inference of deep neural networks, I guess. So if our purpose is to construct is to inference for the value, then basically when we use those deep neural networks for estimating the Q function or estimating the density ratio function, so basically we only require those neural networks to satisfy certain conditions in order to conduct valid inference results for the value. On the other hand, I guess if we want to directly use those deep neural models to inference for the Q function, then this will be very much difficult because we need to derive the asymptotic distribution of those deep neural networks. And in the literature, I guess when in a single stage study, or when we only use a single layer neural network, there are some papers that establish the limiting distribution of the neural network estimator as using like mean field series, so as a solution to some to certain to certain ordinary differential equations. But it remains uncertain how to conduct the statistical inference in that case. I guess this is a very interesting research direction, just to come up with inferential procedures for those deep neural network models. And for the second question, I agree that cross-fitting is always always an issue, and when we do cross-fitting, usually we will average all those samples in order to get full efficiency. And usually we will do cross-fitting over the trajectories because the data trajectory, they are independent. But of course, I guess it is also possible to do cross-fitting over the time horizons. So in that case, we will need to do cross-fitting so first do training on one batch of data and do fitting on the next batch, and then combine those observed data so far to do the training, and then do the evaluation on the next batch. So I have some papers on doing cross-fitting over time horizons in this way. And as for the choice of the discounting factor, I think this is a very this is a very very difficult choice in practice. And in the ride-sharing application, I get so although we consider a discounted setting, but I guess in practice, it might be also useful to consider average reward setting. So in that case, there's no need to choose this discount factor. But in mobile health application, I guess you'll be it might be good just to listen to the clinicians to ask them about their choice for the discount factor. And the hyperparameter tuning and the model selection, I guess this is always a very difficult problem unless we do some cross-fitting. Otherwise, it is very difficult to choose those parameters. And finally, statistical inference under adaptive design. I think this is a very important question, and I have seen some related works, but and many data sets are naturally generated under adaptive design. So so I guess it will be very interesting to conducting statistical inference under this data generating process. And there are some papers that use inverse propensity score weighting in order